Welcome to calculating the pH of weak acid solutions. So we've already talked about how to calculate the pH of strong acid solutions, and those are relatively simple calculations for us. But weak acids get a little bit more complex. So because weak acids are only partially ionized in an aqueous solution, we don't get to make that assumption that the acid concentration is equal to the hydrogen ion concentration. That's no longer going to be true, because only some of that weak acid is going to be dissociated, so those concentrations aren't going to be equal anymore. So there's a mixture of ions, our dissociated acid, and our unionized acid in solution, which means we've got an equilibrium between our HA, our undissociated acid, and our H plus and A minus, our dissociated acid. Right? So we've got a mixture of our acid in this form and our acid in this form. Again, our HA there represents some generic acid, whatever it happens to be. And then A minus is the conjugate base of our weak acid here. So we've got an equilibrium here, so we can write an equilibrium constant. So we've got Ka is equal to the hydrogen ion concentration times the conjugate base, A minus concentration, divided by the acid concentration, HA. Again, this is product concentrations divided by reactant concentrations. And here we're calling this Ka instead of Kc because the A there denotes that this is an acid dissociation constant. So the larger our Ka is, the stronger our acid is. So let's go back and look at that equation one more time. So if Ka gets bigger, that means that the ratio of our product of our two product concentrations here is larger compared to the concentration of our reactant. So as Ka gets bigger, we have more of our acid that's dissociated. So that means that as Ka gets bigger, we're making our acid, or the acid is getting stronger. So if it's a strong acid, then Ka is very large. If it's a really weak acid, then Ka is very small. So for our strong acids, Ka here is greater than 1. It's something like 10 to the 4, 10 to the 5, 10 to the 8, something like that. For weak acids, Ka is less than 1. It's generally 10 to the minus 5, 10 to the minus 8, something like that. So again, if Ka is large, then our hydrogen ion and conjugate acid concentrations are large compared to the HA, our undissociated acid concentration. And this means that most of our acid has dissociated. So if Ka is much larger than 1, then the acid is essentially completely ionized, and the acid is a strong acid. Because basically, if we have a Ka of, say, 100, then that means we have 100 times as much of these guys as we have that guy, or thereabouts. If we want to calculate the pH of a weak acid, we've got some steps. So first, list out the major species in solution. Second, choose the species that can produce hydrogen ion, and write balanced equations for the reactions producing hydrogen ion. Then, using the values of the equilibrium constants for those reactions that we've written, decide which equilibrium will dominate in producing our hydrogen ion. And then last, write the equilibrium expression for our dominant expression. Then we make an ICE table. Remember, ICE, ICE is initial change in concentration and at equilibrium. So here you're listing out the initial concentrations of our species participating in the dominant equilibrium. Then you're defining the change needed to achieve equilibrium. So you're defining what X is. And then last you're writing the equilibrium concentrations in terms of X. And then we substitute those equilibrium concentrations into our equilibrium expression and solve for X the easy way by assuming that the initial concentration of our acid minus X is approximately the same thing as our initial concentration of our acid. Essentially, we're assuming here that if our acid is a weak acid, then the amount of our acid that has dissociated is small, and that means that the concentration of HA is essentially constant from the start to the finish of our equilibrium. And then we have to check that, so we use our 5% rule to determine whether our approximation is valid or not, whether this is valid. If the concentration of our acid, HA, is changing by more than 5%, then we can't use this assumption, and we have to make our calculation even more complex. And then, if that's good, then we go on and calculate the hydrogen ion concentration and the pH. So let's look at an example. So suppose we have a 1.00 molar solution of HF, hydrogen fluoride, hydrofluoric acid, and the Ka there is 7.2 times 10 to the minus 4. So first we want to list the major species in solution. We know that we have water and we have HF because HF is a weak acid. Next, we want to choose a species that can produce hydrogen ions and write balanced equations for the reactions producing hydrogen ions. Well, we know that water can undergo autoionization, so we can write an equilibrium reaction for that one. We know that HF is an acid, so it can produce hydrogen ions as well. So we have the dissociation, the acid dissociation for the hydrogen fluoride, the hydrofluoric acid. We know that Kw, the equilibrium constant for this equilibrium, the top one, is 1.0 times 10 to the minus 14, assuming that we're at 25 degrees C. We didn't specify, but that's a good assumption to make. We know that Ka for this bottom reaction is 7.2 times 10 to the minus 4, because that was given to us. So next, using the values of our equilibrium constants for the reactions we've written, we want to decide which equilibrium will dominate. Well, the Ka for HF is much, much larger than the Kw for water is. It's 10 orders of magnitude higher, and that means that HF will be the major source of our hydrogen ions in solution, which means we're going to ignore the autoionization of water. So now we want to write the equilibrium expression for our dominant equilibrium. So Ka, which we know is equal to 7.2 times 10 minus 4, is equal to hydrogen ion concentrations times the fluoride ion concentration divided by the HF concentration. So now we want to make an ice table. So we know the initial concentration of HF is 1.0 molar. We know the initial concentration of hydrogen ion is 0. We know the initial concentration of fluoride ion is 0. If we react away, if we dissociate X amount of our HF, we're going to form X amount of H plus and X amount of F minus. And that means that our ending concentration, our equilibrium concentration of HF will be 1.0 molar minus X. Our equilibrium concentration will be 0 plus X, so positive X. And our ending concentration, our equilibrium concentration of fluoride will be 0 molar plus X, so plus X. Now we can substitute these equilibrium concentrations into our equilibrium expression. So we already had Ka equals 7.2 times 10 minus 4 molar equals these guys. And now we know the value of each of these guys here, right? So we can plug in X for hydrogen ion concentration, we can plug in X for fluoride ion concentration, and we can plug in 1.0 minus X for the HF concentration. So now we want to make an assumption, because now we basically have a quadratic equation, and we can either use the quadratic formula to solve this, or we can try to simplify it using chemistry and make the math a little bit easier. So we're going to assume that our acid concentration, that 1.0 molar minus X, is approximately the same thing as 1.0 molar. So as long as X is small compared to 1 molar, then this assumption will be valid. So HF is a weak acid. We're going to assume that very little of it is dissociating, and this means that X is small, and that means that now this 1.0 minus X we can replace with just 1.0. And basically this X is small with respect to that 1.0, and then if it's negligibly small, then we can ignore it. And that means that this fraction is approximately equal to that fraction. And then from there, we can say that we can solve this for X squared. So we know 7.2 times 10 to the minus 4 is equal to this fraction. Well, we can multiply by 1.00. Not going to change the value any, but and that means that we now have 7.2 times 10 to the minus 4 times 1 is equal to X squared. And then if we take the square root, we get x is equal to the square root of 7.2 times 10 to the minus 4, which is 2.7 times 10 to the minus 2. But remember, we need to check our assumption and see if it's valid, so we need to use our 5% rule. So, is 2.7 times 10 to the minus 2 less than 5% of our initial HF concentration? So, is x less than 5% of our HF concentration? Well, we know that x is 2.7 times 10 to the minus 2. The initial concentration was 1.0. 2.7 times 10 to the minus 2 divided by 1 times 100% is 2.7%. So we're good, because 2.7% is less than 5%, so our assumption is valid, and we're going to be close. We're going to be off a little bit, but not by much. So now we can go on and calculate the hydrogen ion concentration and the pH. We know the hydrogen ion concentration was equal to x, and now we know that that's 2.7 times 10 to the minus 2. So we plug that into our pH formula, and that gives us a pH of 1.57. So that was calculating the pH of weak acid solutions. And we can do a similar thing with weak base solutions as well.